We'll talk about, let me get this thing on. There we go. So the question on the floor is, why do all this stuff work? So let's pick on you. Tell me what you see up here.
I see the top two are pictures of 3D busts of face.
What are they made of?
What are they made of? The left one might be either wax or some kind of marble sort of thing. Middle one is gold or some sort of thing, and the right one looks like plastic.
And what do you see in the bottom?
Cup, a glass cup, 4 like cylinders with different cloths draped over them, and then a fuzzy looking knot thing.
What's it made of?
Some kind of, it looks like fur, sort of something, yeah, something fuzzy.
Yeah, this was my attempt to copy Monsters, Inc.
Oh, okay.
So the question that we're going to deal with over the next 3 lectures is first of all, do all of you agree with what he said about these things? Particularly this one. How do you know it's wax? Just looks like wax.
Yeah.
You don't agree?
I disagree. I think it's marble.
They're both very similar materials. What makes marble and wax different from, say, this shiny plastic?
I don't think of wax as shiny.
It can be. The difference is both marble and wax are translucent. Light can get inside it and get scattered around inside. We'll talk more about that later. But anyway, what we're going to worry about the next 3 lectures is how we're able to make these judgments. So today, I'm going to start by giving you another part of the history of art where this kind of technique, which you see here in Italian, it's called chiaroscuro. It's an Italian word that means light and dark. And it's an important source of information for painting, even going back before the Italian Renaissance, but it really got perfected after that, and we'll talk about that. And then we'll talk a little bit about the physics of how light interacts with different kinds of materials. Because that's not only can we get the shape of objects from the pattern of shading, we can also get the material properties. In addition to that, I have to plug this in. So here are the 3 properties, 3 things that can affect the structure of light at a point of observation. So you have the 3D structure of the observed scene, the shape of objects. We get that from shading. We have the surface materials in the observed scene, how they interact with light. And then we also have the overall structure of the light field. And all of these things, well, not less the light field than the other 2. We can perceive all of these things when we look at a scene. We know something about the nature of the lighting, we know something about the nature of the materials, we know something about the nature of the surface geometry. And what we're going to try and understand over the next 3 lectures is how we're able to do that. Now, one of the first people to talk about this in psychology, which a guy by the name of James Gibson, I've mentioned him several times already in this course. He was one of the first people in psychology anyway, to appreciate the complexity of how light behaves in natural scenes. And so one of the things he points out in his book is that if we have a single light source here, right, the light hits the walls, it hits the table, and each time it hit a surface, it reflects in many different directions. And one of the interesting things about that is that light actually fills the volume of space. So if you took a photometer right, and you measured in this room at any given point, there'd be some flow of light passing there, more in some directions than in others. And we'll talk a little bit later about how one can measure that and how we can make use of that information. So the nice thing about this is what Gibson pointed out is it doesn't matter where the observer is. So if I'm here, there's a pattern of rays that are impinging on my eyes that lets me see the world. And if I come over here, right, I've got a different pattern of rays that are impinging on my eyes. So wherever you go, there's always a pattern of light that's available to stimulate your eyes. So let's start the lecture today. I want to talk about chiaroscuro, which is a technique used in art. Now I know a few of you have taken art classes before. Raise your hand. Did they teach you about chiaroscuro? Do they call it that? Yeah. So it's still around today. And we'll talk a little bit about the history of that. So the main thing to keep in mind here, note that the steepness of the shading gradient conveys information about curvature. So where the shading is varying really rapidly, that's telling you about curvature. Now that's different from texture or linear perspective, which is telling you about depth or slant. So shading is actually getting at the second order structure of objects. It's telling you about curvature. If you get shading on a planar surface, as we'll see in a second, you don't get much information at all. Shading is all about curvature. Now, if you look at medieval shading, there are a couple things. There are no light source, or the light source is at the eye of the viewer. A couple of techniques they used. They would change the shade, add black as the surface faces away from the viewer. They change the tint, add white as the surface faces the viewer, or they might change the saturation of the color. And so here's an example from Cimabue, Madonna and Child, and this is early medieval shading. Now, anybody reading the paper, there was a recent painting by Cimabue that was just discovered. Things worth hundreds of millions of dollars property that was in somebody's barn that they discovered. But it's a cool story. Those things actually happen. Here's another example from Martini. Again, this is pre-Renaissance, pre-linear perspective. There's no linear perspective here. The size isn't right. There are all kinds of things wrong with this painting. But if you look down here in the cloth, you see how when the cloth becomes concave, the surface is darker, and then when in convex regions, they make it lighter and less saturated. All right, so these are some of the cues they realized early on in Italian art. Now, it was really in the Renaissance that chiaroscuro really came into being, and this is probably one of the more famous paintings in the world, the Mona Lisa. Anybody actually seen the Mona Lisa? Have you been to the Louvre? I've never seen it myself. Is it impressive?
Mm-hmm. It's much smaller than you'd expect. That's what.
Oh, no kidding.
Yeah.
So this was done by Leonardo da Vinci. Leonardo da Vinci was an amazing guy. He wrote notebooks. One could argue that he was perhaps the first perceptual psychologist. So he actually did experiments where he would take objects and illuminate them from different directions and with different intensities, and he'd draw out how the shadows behaved when you do that. And this picture sort of captures that. It doesn't really have any sharp lines. He's using shadows to define everything. All right, so this is an example, a really good example of chiaroscuro by one of the masters of it, which is Leonardo da Vinci. Now here are a couple other early examples. This is one by a French artist named Jean Fouquet, and this is a Dutch artist, Van Eyck. I want you to pay attention to this one first. Anybody notice anything unusual about this? Note the title, Virgin and Child Surrounded by Angels. So what's unusual about this painting?
More of a 3D depth.
I'm sorry?
More depth to it.
Well, just the person that's being depicted.
Mary, but it's very promiscuous Mary, maybe. Virgin child, I don't know. Virgin child, you know.
How many bare-breasted Marys have you seen before?
What?
How many bare-breasted Marys have you seen before?
Maybe it was pop art back in the 50s. I don't know what they
If he had been in Italy and painted this, he would undoubtedly be executed. But you can get away with this in France. The other thing is, why is her head bald? Any ideas about that?
He couldn't paint hair.
I'm sorry?
I said he couldn't paint hair.
Yeah, but why would she shave herself bald? Well, what was a problem back in the 1500s? Did people were they particularly clean? There was a real problem with lice. And so it was common in those days for rich women to shave their heads and wear wigs instead of having hair to avoid problems with lice. And the other thing you'll notice is how pale she looks, almost completely white. Any idea why that would be? Yeah.
I mean, if you go back to the idea of wealthy people, they would stay indoors, it would be more for like peasants and, or maybe it's like the whole Virginia.
Yeah, you're close. So the rich people back then didn't want any sign that they ever did manual labor in their whole lives. And so one of the signs of doing manual labor is you get a tan, your skin gets darker. And so to contrast from the plain people, what the rich people would do is they put white powder all over themselves, so they look pale. You can see this in a lot of period costume pieces where they have that same tint. Now, there are a couple of other things about this painting. The guy is not particularly skilled, so if you look at the cloth, it doesn't look very soft. And Mary's breast looks like it's growing out of her armpit. And the baby here doesn't look exactly baby-like. But the composition of this thing is amazing. I actually saw this painting. I've seen it a couple times. It's in a museum in Antwerp in Belgium. And I was on the other side of the museum from where the painting hung. And I just couldn't take my eyes off it, so I just kept walking to it because just the stark, I mean, it looks like something Salvador Dali would do. But once you read about it, it makes sense. Now, the other thing to note about this woman, the name of the model in this is a woman named Agnes Sorel, and she was the mistress of King Louis. So everyone in court would have known who she was. And that she was a mistress. So, I mean, to paint her as the Madonna, I mean, would truly be scandalous, but apparently Louis didn't care all that much. And now Van Eyck is a much more skilled painter. So the chiaroscuro is better here, the cloth is better defined. This has nice composition, but nothing like the wow factor that this one does. Now, over time, people got a little bit more skilled at this, and that brings us to Caravaggio. Caravaggio was sort of a scoundrel. He would get arrested all the time for brawling in bars, but he was the founder of a technique which is called tenebrism. And tenebrism is like chiaroscuro on steroids. It's really exaggerated light and dark. Now, at about this time, the Catholic Church was facing competition for the first time. This is right when the Reformation was occurring. And so because of that, the Catholic Church wanted to jazz up their religious art and make it look more dramatic. And the way to do that is by really accentuating the contrast between light and dark. So this is one of Caravaggio's more famous paintings. The most famous one of all, though, is this one, Death of a Virgin. Now, this painting was originally commissioned to hang in a church. And when Caravaggio presented it to the friars of the church, they took one look at it and said, "We're not paying for this, take it back." Now, there are a couple of, if you look at art history, there are a couple of reasons why people speculate that once. One is that Mary's shown here with bare feet and her legs are showing. That was not proper decorum at that time. And so some commenter said it looked like he had a prostitute model the Virgin Mary. Caravaggio denied this, but I think the real reason why it was turned down, though, was the basic idea that Mary died and had a corpse. So a lot of the religious leaders then said, no, Mary was assumed into heaven. And so the painting that they commissioned after they turned this one down, that's what it depicted as Mary being rising into heaven surrounded by angels. I think that was the problem they had with this painting. Here's another example of tenebrism. This is a Belgian painter, Rubens, with Samson and Delilah. Notice the really bright light here and goes to dark, this really high contrast. This is the hallmark of tenebrism. Yeah?
Is just really high contrast the main distinction between tenebrism and chiaroscuro?
Chiaroscuro, let me go on. I'll tell you. So after tenebrism sort of fell out of fashion, only around for about 50 years, you'll see the same chiaroscuro. It's just not as stark. Okay. All right, they soften it, which is more natural. So these scenes typically are filmed at night, so there's a bright light that's shining directly on one part of the scene. Other parts are completely in darkness. So these are usually nighttime scenes with close-up patterns of illumination to get that effect. Here's probably my favorite. This is a Dutch artist, Van Honthorst. I have no idea how to pronounce it, but he traveled to Rome to learn from Caravaggio, to learn this new technique. And this is an example of his. So if you've ever heard the expression, Jesus is the light, well, that's the embodiment of it in this particular painting. So where's the light coming from in this painting? Where's it coming from? It's coming from Jesus, right? Jesus is illuminating everything else. Now, as I said, this fell out of favor after about 50 years or so. It come much more back in favor. Caravaggio is revered now, but he had this resurgence in the 20th century. Here we have later paintings, later in the 1600s. This is William Drost. Right, so getting back to your question, it's the same nighttime scene, but notice the shadows are softer, the lighting is a bit softer. This is truly skilled painter. The cloth, you can almost see how soft it looks. I mean, cloth is one of the great tells of a really master painter. It's hard to do, and some people do it really well. Drost is a good example of that. And here's one of my favorite paintings of all time. You also see the same thing, the nice cloth. Again, the lighting is much softer than you would see in a Caravaggio painting. This is called The Girl with a Pearl Earring. There's actually a movie about this. I can't claim it's a great movie. I watched it with my wife and drove her crazy because each time they would show a painting, I would be on, yeah, here, this is the one, and tell her the story behind the painting. And she said, well, you shut the hell up. Let me watch the movie. All right, so what it is we're going to do for the next week and a half is we're going to try and understand why this works. What is it about that shading that's telling us about the material? What is it about the shading that's telling us about the shape of objects? That's what we want to figure out. Now, this is a really new area of research. It really, especially the material part, it really wasn't possible at all until the advent of really fast computers and modern computer graphics, which allow you to simulate this stuff in a physically realistic manner. And I'll show you a number of examples of that. I've been doing research in shading for, geez, back to the 1970s. I got into it completely by accident. There was a new technology that came out right about then called raster graphics. Any engineers in the room know what that means? All right, so in the old days in computer graphics, it was based on oscilloscope technology. So if you wanted to draw a square on the screen, you'd had a cathode ray tube and an electron beam, and you would program the beam so it moved in the shape of a square. All right, so literally the beam would trace out the shape that you're trying to depict. And people did research on that. So the first computer graphics setup, I think, was in the early 60s. Psychologists started using them almost immediately. And that was, and so I was one of the people in graduate school who did that kind of stuff on a computer that was, you know, about the size of that podium, cost $50,000 and had 25K of memory and a paper tape input for a reader. I'm really old. But in any event, a friend of mine suggested that we get one of these new raster techniques. What raster graphics did is it combined computer graphics with television. And the reason I wanted to do that, because at the time I was mostly doing research on motion, and I wanted to be able to easily videotape all my stuff. And so the guy asked me how many, let me say more about the raster graphics. So the way that works is, with the electron beam, it just moves in a series of lines. Always the same, doesn't matter what the picture is. And then you have a large amount of memory that defines the intensity of the beam at every position on the screen. That's called a frame buffer. And so when I was ordering this stuff, the sales guy said, well, how many bits of memory do you want for the frame buffer? And I said, well, why would I need more than one? Because I was used to the technology where the light's on or it's off. That's all you could do. But the whole purpose of raster graphics is to get variations in grayscale. So apparently when they shipped the computer, the guys in the shipping department said, well, this is crazy. Nobody would order one of these machines with one bitmap, with one plane of memory. That's ridiculous. So they shipped it with 8. And then I had a couple of graduate students and said, oh, gee, we have to start playing with this. And so it's completely by accident that I got into this line of research, because my students insisted that we had to play with this new piece of equipment, and they shipped me more than I had ordered in the first place. All right, I'm getting off on anecdotal tangents. Let's talk a little bit now about physical measures of light. So there are several of these that you need to keep in mind here. One is called luminous flux. It's light per unit area per unit time. So if this were a photometer and I hold it up, and what the photometer does is, say, take all the light that's coming in from this angle, and it measures, all right, how much light is coming in per unit time, per unit area. Illumination is light that falls on a surface. Right? So luminous flux is the light that's just traveling all through the room. You can't really see it. You can only see it when it interacts with surfaces. However, let's say I take this flashlight and I can illuminate you. All right, so illumination is light that falls on a surface. Luminance is the light that reflects from a surface toward your eye. So if I perceive your shirt as white, it's because it has a high luminance. It's reflecting a lot of light toward my eye. Whereas if I see your shirt as dark, that's because it's reflecting relatively little light toward the eye. So luminance is the light that comes off a surface toward the eye. Reflectance is the proportion of the incident light that's reflected. So dark things have low reflectance, white things have high reflectance. Luminance is the product of illumination times reflectance. So one of the problems that we'll be discussing a little bit this time, but more next time, is how do I know that your shirt is white and your shirt is dark if I turn down the lights? Right? So you could have a white thing with very little illumination have the same luminance as a dark thing with very high illumination. And so one of the basic problems that people studied for a long time is how are perceptually we able to tell them apart. This is a phenomenon called lightness constancy. Our perception of lightness doesn't really change that much if you alter the light levels. And so people have tried to figure out why that's the case. Now, I want to do one more demonstration, and this is particularly important. We can do it over here. And that is how the illumination varies with the angle of incidence. So let's say I take this flashlight. Don't tell me it stopped working now. I guess I'm not going to show you this demonstration.
I have a flashlight, does it matter what it?
Oh, can I borrow it?
Yeah. It's got two beams though here. That's the bottom one. And then
Yeah, that's the one I want, is the second one. Okay, so let's say I shine the flashlight. This is actually better flash than the one I brought. Notice the area where the light is on the surface. So if the light is pointing directly at the surface, it's focused on a relatively small area. Remember, illumination is light, amount of light per unit area. If now I take the thing and I do this, the light is spread out over a much larger area. So what that means is the same amount of light, but it's spread out over a larger area. That means the illumination is lower. And we're going to see this principle. Could you pass that back to her?
Yeah.
Thank you. Thank you. So you can see that here. If the light is directly perpendicular to a surface, it projects a relatively small beam. The beam projects a small area on the surface. But if it has an incident angle like so, then it's spread out over a larger area of the surface. And this leads to a law called Lambert's law. It's the main reason why chiaroscuro works is that things that are closer, things that are perpendicular to the light source will be brighter than things that are perpendicular to the light source. Why is that? Because the illumination is higher. That's the reason. So we can see that here. So we look at this cube-like shape. This region is the brightest because it more closely faces the light source than this region, which is at an orientation that's farther away from the light source. And so that's why you get these patterns of shading here, because the luminance varies systematically with the angle that the light is hitting the surface. So that leads us to another important distinction that we need to make, and that is the difference between lightness and brightness. So if I'm measuring the light coming off your jacket with a photometer, I'm measuring brightness. But if we're asking an observer, is his shirt dark or light, then we're making a judgment about lightness. So lightness is a perceptual property, whereas brightness is a physical property. Actually, I take that back. Brightness is a perceptual property too, but it's the perception of how much light is getting in your eye, as opposed to lightness, which is a perception of what's the color of the surface that you're looking at. They're two different things. All right, so now let's get into light-surface interactions. And here we'll start to see some of the power of modern computer graphics at work. So matte reflections, which would be most of the clothing that all of you are wearing, what happens is light hits a surface, and the surface scatters the light in all directions. I'll say much more about that as we go along. Specular reflection, on the other hand, the light bounces off a surface like a billiard ball, so it's only reflecting over a narrow range of directions. Indirect reflections occur when, for example, let's say we have these light bulbs up here, and where are they shining light? Where are the light bulbs shining light?
Kind of generally downward.
Right, but they're also illuminating the walls, right, in the back? And what happens to the light when it bounces off the wall? It can illuminate other objects. All right, so what indirect light is light that has come from a direct source, reflected off one object, and then that object serves as the illumination for another object. And I'll show you a couple of clear examples of this in a little bit. Transparency, light passes through a surface and is refracted. So glass would be a good example of this. And translucency, light passes through a surface and undergoes subsurface scattering. So this would describe things like marble and wax. All right, so light or skin is also translucent. So why do people get red cheeks?
Embarrassment.
And what does the embarrassment do?
Blood to your face.
Cause blood to your face. And why does that make your cheeks red? Because the light gets inside, interacts with the blood, and then comes out with a reddish tint to it. Here's a good example of indirect reflection. You see this sort of cyan color on the floor here? That's light that's reflecting off this box and hitting the floor. And you can actually use that as a source of information. So if I raise the box off the ground like that, you see the indirect light becomes separated from the base, and that's information that's telling you this thing is levitating above the ground. Now, there's another situation in lighting where if you're looking at a cloudy day, what is the pattern of illumination look like? So in a cloudy day, right, the light's coming from the sun, but when it hits the clouds, it gets scattered like crazy. And so by the time it gets down to Earth, you're getting illuminated from all directions at the same time. And the main thing that determines the intensity of reflected light in that case is a concept called vignetting. So the idea is the more of the sky that a region can see, the more light that it's going to receive, more illumination it receives. All right, so in concavities, right, where you can only see a narrow swatch of the sky, it gets less light than you would see in convex regions like the tip of my nose. However, the intensity is also affected by the angle of incidence. So you got two things going on. You got one is the light is being controlled by how much of the sky is visible from that point. And the other thing that's happening is what are the incident angles at a given point. And so here is an example of that. So here we have the light's coming, the light in this case is directly in front of the object. Here is an angle of 35 degrees, here it's an angle of 70 degrees. Notice that you get this bright spot at the bottom of the concavity. That's due to the angle of incidence there is 0, which is where you get the highest illumination. Then notice the walls of the concavity are darker than the walls on the concave regions. And that's because of vignetting, because the concavity sees less of the sky. It's more pronounced here than it is there with a point light source. Clear example here. So here we have, again, a convex region. You see this region is darker than the outer side of the ridge here. Why is that happening? How much of the sky can you see inside here? Only a pretty narrow angle. So it's not getting that much light. Whereas the outside sees much more of the sky. And that's why this region is brighter than that region. Okay? So this is, again, called vignetting, and it's determined by how much of the sky is visible at a given point. Now, this also interacts with inner reflection. So if you look over here, it's exactly the same scene, only this surface reflects 50% of the light. This surface reflects 90% of the light. And in this case, what happens is the light gets trapped inside this concave region, which causes it to brighten up. All right, so you've got two conflicting things going on. One is vignetting, which is causing convex regions to be darker. I'm sorry, concave regions to be darker. And then you have surface inner reflections, which are causing concave regions to be brighter. All right, and both of those things work together. So depending on what the reflectance of the surface is, one of them will be more important than the other. So to give you a sense of how important indirect light is, this is a scene with, there's one light in this scene, but like in your house, so in your living room at night, where does the light come from?
The windows. The windows.
At night.
The light.
Do you have lamps?
Yeah.
You have lamps. And when your lamp, do you just have a bare bulb in the lamp, or do you put a shade over it?
The shade
Put a shade over it. Why do you put the shade over it?
to make it.
Because it's annoying as hell to look at a bare bulb that's bright. And what does the shade do? The shade prevents the light from shining directly on most of the things in the room. So what you're really seeing is the stuff that comes out the bottom and the top of the shade that's bouncing off the floor, that's bouncing off the ceiling, and then it bounces off other surfaces, and that's what illuminates the room. It's illuminated by indirect light. So in this particular case, I have a scene, a living room. There's one light in the scene, and it's behind a baffle, which is behind the camera. So there's no direct light in the scene whatsoever. And this is what you get with one indirect bounce. Hardly any light at all. But now let's increase it to 3 indirect bounces. Now you can see the living room. And we'll increase it to 5 indirect bounces. Now it looks even brighter. Now we'll go to 10 indirect bounces. Even more. How about 15 indirect bounces? See it whitening up? And now we'll go all the way to 100. Now, one of the things that happens when you do this is that as you increase the amount of surface inner reflections, the variance of the luminances goes down. So in a black room with a bright light, you have really stark contrast. And there's a famous experiment by a good friend of mine at Rutgers named Alan Gilchrist who showed that if you have all the surfaces in the scene have exactly the same reflectance, you can tell the difference between black and white rooms based on that property. Because you've got smaller variance in the light for the white room than you do for the black room. But the main thing I want to point out here is that you can get a lot of lighting from indirect light, and we typically do in indoor environments. Less so during the day and we're outside because you have the sun. All right, let's say something a little about surface materials. Do we have something shiny in the room? Anybody got something shiny? Oh, that's perfect. Why don't you hold up the water bottle? All right. What's the difference between her water bottle and her sweater? Right? You see the water bottle is metal, right? And how would you describe her sweater? It's matte. So the main distinction there is how the material interacts with light. So when the light hits the metal, it bounces off like a billiard ball. And you get those specular highlights. I can't really point to them because everybody in the room will see them in a different place. Her sweater, on the other hand, scatters the light. And that's what gives it the matte appearance. So let's say I took the metal surface and I took her sweater and I put it a small patch under an electron microscope and blew it up by 1,000,000 times. What would it look like? Well, polished metal, this is 10 million times. So polished metal, the surface looks smooth when you blow it up by 10 million times. That's what's causing the specular highlights. On the other hand, this is construction paper. This is blown up 100 million times, so the blow up is greater here than there. But you see all the nooks and crannies of the fibers that the paper is made out of. Right? So when light hits that, it's hitting at different incidence angles and bouncing off in different directions. And that scatters the light, and that's what makes it look matte. And so if we look at this in terms of perceptual appearance, by the way, the parameter used in computer graphics to define this is called roughness. It varies from 0 to 100. So 0 means surface is perfectly smooth, it reflects light in one direction only. Roughness 100, this is sometimes referred to as a Lambertian surface, and it scatters light completely. All right, so you have uniform distribution of reflectance in all directions. And this is the difference in appearance. So small roughness, we get this really shiny looking material. And high roughness, we get this matte looking material. So notice the perception. Now what's fascinating about this is the difference that's causing the difference in appearance is happening at microscopic scales. Right? So it's determining how light interacts with the surface at really tiny scales. And somehow we're able to determine that, look instantly and say, yeah, that's a matte surface and that's a shiny surface. And so we'll spend some more time later talking about how exactly we're able to do that perceptually. Now, some objects, like say a shiny coffee cup, a shiny ceramic object or shiny plastic, or high gloss paint, you basically have two different kinds of reflection at the same time. So objects like that, you have both light that's scattered and light that bounces off like a billiard ball. And the best way to think about that is, suppose I've got a really rough surface and I cover it with a clear coat of varnish. Right? So the varnish is perfectly smooth and it's going to reflect light like a billiard ball, but it's also transparent. So light can pass through it and interact with the material underneath. Paint works in a similar way. So paint, traditionally is composed of two kinds of molecules. There's what's called pigment, that gives the paint its color, and there's what's called binders, which hold everything together. Now the binders are transparent and the pigment is not. And so what happens is if you have a relatively small proportion of binder relative to pigment, then the pigment lies below the surface. The light passes through the binder, then reflects off the pigment. If the pigment has a higher percentage of molecules than the binder does, then the pigment rises up and covers the surface and it reflects something that looks like that. All right, so here we have the specular reflections in green. They're just bouncing off the surface. And then we have the what's called diffuse reflections, where it's interacting very slightly inside the surface, which is scattering light coming out. And what you get from that is something that looks like this. So does this look like a shiny plastic? All right, so the reason it has this appearance is you've got these two kinds of reflections that are added together. Now this is a little bit clearer if you add color to the mix. So here's an example where you have the diffuse reflections only. So this is reflection where the light is completely scattered by the surface. These are the specular reflections only, right? So this is the light that bounces off the surface like a billiard ball. So this is happening off the smooth, transparent layer, and this is the rough stuff that's underneath that layer. And look what happens when you, so this doesn't look like much of anything. This doesn't look like much of anything. But if you mix them together, you get this amazingly shiny surface. Now, the thing I want you to note about this is that the diffuse reflections are the color of the surface materials, and the specular reflections are the color of the light source. Right, so you get a color separation when you have those kinds of materials. Now, it turns out that you can take all the materials in the environment and separate them into two categories. So there's one that's about 90% of all the materials you'll see in nature are called dielectric materials. I'm not exactly sure where the term dielectric materials comes from, but these are materials that do not conduct electricity. They act like insulators. What I've just described to you here is the behavior of dielectric materials. So for dielectric materials, the color of specular highlights is always the color of the light source. The surface color has nothing to do with the specular reflections. The other class of objects is about 10% of the materials you'll see in nature are called metals. And metals are a little bit different. Metals, the surface color will affect specular reflections. And here's an example of that. So what does this look like to you?
Copper.
It's a simulation of copper. That's what it is. All right. The light here is all white, right? So the illumination is white. So the copper color, and there's no diffuse reflections here. It's entirely specular. The other thing about metals is that any light that's transmitted into the surface gets absorbed, right? So metals are completely specular. They have no diffuse reflections at all. But then the question is, where is this copper color coming from? And the reason is because in metals, the color of material can affect the specular highlights. So dielectrics are the most common ones, do not conduct electricity. And in those cases, the specular highlights are always the color of the light source. Metals do conduct electricity, and the color material can affect the specular highlights for metals. So one line of research we're going to talk about a little later is how can you tell those two classes apart? So you instantly recognize this as a metal, right? The question is, how are you able to do that? Now that gets us to another way thing that can affect reflectance, which is called anisotropic reflections. So you remember what anisotropic means? It means it's different in different directions. And you typically get this with many cloth materials like satin, right? So the way it works is you have the strands of fiber that are making up the cloth. And what happens is the light, if it's parallel to the strands of fiber, reflects in a specular way. And if it's perpendicular to the fiber, it reflects in a diffuse way. And so here are some examples of that. So here's an example of linen, and this is a blow-up. In order to simulate this stuff, by the way, the research had to go in and actually model the individual fibers of the cloth and the nature of the weave. Right? So all of those things play into how this thing appears. So this is polyester satin charmeuse. I have no idea what the hell that is. I think it's those things women wear, very clingy dresses, are made of that stuff on a special occasion. And because the weave's different on the front and the back, if you look at the front part of the surface, it looks a little different than if you look at the back part. All right, you get a similar effect as this is brushed metal. Again, you have really fine grooves in a metal. You'll get anisotropic reflections like this. All right, so that brings us to light transmission. So here I have an example of glass. What happens here is that light hits the boundary between air and glass. And in the case of glass, a large chunk of it, a little bit of it is reflected. More of it is transmitted into the glass. But it changes direction. You've all seen the stick that looks like it's bent when you stick it in water. That's the effect of refraction. And so this is what you get here with glass. Translucent surface involved this thing called subsurface scattering. So this is something like wax or marble. The light gets into the surface, is transmitted inside, but then it bounces around off the molecules on the inside before some of them get back out. And that gives you the impression of translucency. So if you look at this object right here, if the material's thin enough, you can see what's behind it. But for the fat parts, you can't really. You also see this brightening around the corners. That's probably the primary source of information that's telling you this is a translucent object. Well, that and seeing the checkerboard here with reduced contrast. So these are all the kinds of optical phenomena that we have to deal with. And somehow we make sense of the world by doing all that. Now what's interesting is if you simulate this stuff, you need A, a really fast computer, and B, you need really sophisticated software, because if it's not done right, the perceivers know it pretty much right away. Especially glass. Most renderers really don't do a good job with glass because they don't let enough interreflections happen on the inside of the surface because they're trying to save computation time. And that brings us to this. I figure after boring you with a little physics, we'll bring back something that will make you smile. How many of you see the dress as blue and black? Raise your hand. How many of you see it as white and gold? Raise your hand. So white and gold people are in the minority. So the first time you saw this and somebody said it was blue and black, did you say you're stark raving mad?
Yeah, I was like crazy. I don't know how you can even see blue and black. It's clearly like gold. I don't know.
Well, I'm going to save this for next time. I'll explain to you why this works. But I just want to give you a taste because we're going to start on a new topic. So I've introduced you to sort of the history of chiaroscuro. I've given you a brief overview of some of the underlying optics that makes it work. And now we're going to spend the rest of the time trying to figure out how we get information from patterns of shading that tells us stuff about the environment, like the color of that dress. The one thing that everybody agrees on in this dress it's ugly as hell. Apparently they made like 5 versions of it. When I was off in Europe early in the term, I was talking with a woman who's one of the world's experts on color vision. And when this came out, she actually bought 5 copies of the dress in different combinations to play around with. But I'll come back to that later. This is just a teaser slide. So the thing I want to worry about now in the beginning of next time is what I defined earlier as lightness constancy. So what this is how is it that I can perceive the color of the surface and have it appear to be the same when I change the amount of illumination? So if I raise the light, you're getting more luminance from the surface, but you don't see its lightness change. And so the question is, how is that possible? So one of the first experiments on this was done by a German professor, a guy by the name of Gelb. And what he presented observers with a black disc, like so, and he had a spotlight that the observers couldn't see. And if you shine the spotlight on the disc, turn the spotlight on, the observers would say, oh, the disc is white now. But then, if you took a piece of white paper and you stuck it in the beam, now the paper looks white and the disc looks black. Right? So you got this thing that looks white, and you take a piece of paper and you just move the paper in front, and all of a sudden the white thing switches immediately to black, and you see the paper. The good friend of mine at Rutgers, I was telling you about, Alan Gilchrist, has a really cool way of demonstrating this. He does it in a large auditorium. I've never had the nerve to try and pull it off myself. But what he has is a sequence of papers that range from white to black. And then he has a projector that they're all in little compartments. And then he has a projector that's shining light on this box with the little compartments. And the observers can't see it. So the light's only shining on the compartment, not on anything else. And so now he opens up the compartment that has the black paper, and observers report it's white. Why would they do that? It's receiving much more light than anything else in the room. And so we have one default option that says the thing that's reflecting more light than anything else is white. And you're not going to consider the possibility that there's a spotlight. Your shirt is really black, but there's a spotlight shining on it, which makes it reflect more light. So he's got this black card you're looking at. Everybody in the room hollers, it's white. So then he turns over the next card, which is a gray card, dark gray. And people go, oh, that one's white. And the other one now is turned to gray. And then he turns over the next card, and people go, oh, that one's white, and the others became a little darker. And then finally he gets to the white card, and the first one, which originally looked white, now looks completely black because you've altered the illumination. So that's basically what the Gelb effect is doing. It first looks black, you shine the light on it, it looks white. You put a piece of paper in to provide a context, and all of a sudden the disc looks black again, and you see the paper is white. So this is one of the first examples of how we use lightness. Lightness constancy, one explanation of it is that it's based on the luminance ratio between 2 surface patches. So let's say, for example, that your shirt reflects twice as much light as his shirt. Now, if I increase the illumination by 10, it's still going to reflect twice as much light as his shirt. Both of your shirts will reflect more light than they did before, but the relationship between the two won't change. Similarly, if I lower the lights, that same ratio will apply. So by using luminance ratios as a potential mechanism for achieving lightness constancy. Now there's a key assumption in that analysis. Anybody think of what it might be? I sort of hinted at it with the Gelb effect. This assumes both of you are being illuminated by the same intensity light. All right? So if you're in a dark part of the room in shadow and you're in a light part of the room, then all bets are off. And we'll see a couple of illusions that are based on that. How many of you have seen the cylinder checker illusion? It's a famous, I'll show it to you later in the course, or next time actually. So luminance ratio seems to be the way to go in the early days of the 20th century. And there are a couple of examples that people use to demonstrate this. So do these two patches look the same or different? What do you think?
They look different.
Which one's darker?
The one on the left.
All right, now if we're using luminance ratios, you would expect that because there's a bigger ratio here than there is there. And lateral inhibition does something very much like that. So the idea here is that you're getting lots of inhibition from the surround in this case, which causes it to appear dark, and you're getting less inhibition here, which causes it to look lighter. But if I move the squares away, like so, now they look the same. If I move them back, they look different again. So even though you know what's going on, it doesn't help you in this case. And again, I think I showed you this slide earlier. This is just how lateral inhibition is an explanation of that. How many of you see gray squares at the junctions? Have I shown you this effect before? Okay, so again, due to lateral inhibition, I won't go into it anymore, and that's the reason why you don't see it when you look directly at the junction is because the receptive fields in that region are smaller. Now, people had known for a long while that traditional explanation of lightness constancy was not going to hold up. I'll give you one teaser, and then I think I'll let you go early, and we'll come back to this next time. This is a demonstration by Kurt Kafka, who's one of the early Gestalt psychologists, and let's pick on you this time. Tell me what you see.
I see a dark rectangle and a light rectangle, and then like a ring through the middle.
Okay, and is the ring homogeneous gray?
Yeah.
How about now?
No, not anymore.
All of a sudden the ring got darker. You just see it happen just like that. And bring it back, and now it's homogeneous again? All right, so there's something about configurations that, here's an even weirder one. Let's move it a little bit differently. Now that's the one I just showed you. Let's try this. It's blowing your mind? I'll move it back again. Got a homogeneous ring. All you're going to do is slide the thing down like so. And now it looks transparent and darker. All right. You watched it move. I'm not playing any tricks on you here. This is all due to your brain, not to the wily Professor Todd. All right, so now I've given you, I'll tell you what, I'll do one more example and then I'll let you go. It's this one. So who shall I pick on this time? Let's pick on you. Which region looks darker, A or B?
A.
Do you all agree A looks darker? What if I told you they were exactly the same? Not going to believe me. All right, well, here's the test. I've got this rectangle right here that I'm going to move into this region, and you'll see it blend in. And then they'll see what happens if I move it into this region. So let's move it into A. You see it blends perfectly. And now let's move it into B. It also blends perfectly. Now, I have a funny story to tell about this display. This illusion is called the White's illusion. And when professors get textbooks, the textbook manufacturers often give them a set of slides. Actually, nowadays they give them PowerPoint presentations. The worst PowerPoint presentations you'll ever see. They're all words, you know, few images. I hate words in PowerPoint presentation, but even though I have a few here. So anyway, in the PowerPoint demonstrations, they had an example of this White's illusion. And it was the best example of the White's illusion I'd ever seen. And so I set up this demonstration to convince the class that they really were the same intensities. And lo and behold, when I moved it there, I got it to blend perfectly. But then when I moved it over here, it didn't blend. Somebody had cheated, right? I think somebody at the editorial office said, hey, we can make this illusion look better. Let's make this really be lighter than that one. And so I emailed the textbook author and told him what I had discovered. And then when the new edition of the book came out, they had the same figure. They didn't change it. So that was the end of my using that particular textbook. But now, is the White's illusion, you think, consistent with the traditional account of lateral inhibition? Let's look at that more carefully. So let's take this object here, right? So it's getting some inhibition from the sides, no inhibition from the top and bottom. This one's getting the same amount of inhibition from the side, but a lot of inhibition from the top and bottom. So based on lateral inhibition, this is the one that should appear darker than that. Right? So if lateral inhibition is the case, this one should appear darker than that one. But the opposite is what we get. So here's the insight to try and understand this, and this will be the setup for Thursday's lecture. I hinted at it a little bit earlier. That is, let's say I'm comparing your shirt and your shirt. And I can use the ratio of their luminances in order to get the relative lightness. But that assumes that you're being illuminated in the same way. So under what conditions might you not be illuminated in the same way? Right? There are keys that will help you out on this. And I spelled out a lot of them when we did the perceptual organization lecture. So that stuff's going to come back. What do we see here? This kind of vertex. Have we seen that before? What's it called? A T vertex? And what do you know about T vertices? Who's in front of whom? So who's in front? The black or the gray? Raise your hand if you think the black's in front. Raise your hand if you say the gray is in front. All right? Don't see any gray in front. So what this is telling us is that the black and the gray are different depths. And so you might say, well, I'm not going to count, I'm not going to consider that A and the black have the same illumination because one's occluding the other, and that might cause things to change. So in this case, what we're going to do is we'll compare A to this, in which case A is the darker thing along this row, which is all the same depth. Whereas if we do the same thing over here, B is the brightest thing along this row, which is all at the same depth. All right, so we're using context. This is the first example where what the brain is trying to do is partition a scene into regions that are likely getting the same illumination. And it's only applying the ratio rule in those regions. If you have regions where you suspect they're not being illuminated in the same way, then all bets are off. You're not going to compare those in the same way. Now I think I will break here. I will give you several more, well, let me just end with this. So luminance ratio assumes that the patches have the same illumination. And what that means is if you're going to use that, it's necessary to have some sort of grouping mechanism that can isolate different parts of a scene that share the same illumination. Perceived lightness can then be determined by relative luminances within each group. And we'll see that a lot of our lightness perception involves that. We're partitioning the scenes using a lot of the principles that the Gestalt psychologist talked about. And I'll come back more about that next time. So I will see you on Thursday, and I will try my very best to have the exams back by then.